Okay, here is another video, and this time I will be doing the calculator active problems. I'm not going to be showing you my calculator screen, but I'll try to explain what I'm doing. So for problem number 31, we're given velocity, and we're asked about maximum speed. So speed is the absolute value of velocity. We want to see where velocity is either positive and as positive as possible, or negative or as negative as possible. Basically, as far away from zero as it can be. So I'm going to graph this velocity function. I would recommend, if you're going to be doing multiple graphs, just start a new document every time. It is faster than deleting. So x times cosine of x, I'm just calling this x instead of t because that's easier to type, minus the natural log of quantity x plus 2. And so I am looking at my graph, and I will just say that my graph looks something like so. It appears to be farthest away from zero, way down here. I'm actually going to zoom out a little bit. Yeah, and it does something like this. So it is as far away from zero as possible around here. The zero line, just FYI, is like that. Right? Maximum speed is not maximum velocity. It's when your velocity is as far away from zero as possible. So right around here, we have a big negative. Let me figure out where that happened. Sorry, I need to check my window. You don't have to rush through these. You get an average of 3 minutes per problem. So you can be kind of deliberate as you do this. Okay, so yeah, sorry, I misread something. So this happens right before 10. This is between 9 and 10. I can just eyeball that from the graph. So I will believe that it is that value. You could certainly find that by zooming in or doing minimum. Usually for problems like this, the choices are far enough apart that you can tell which one it is just by looking at the graph. Okay, number 32. I will point out many of these problems on the calculator section don't require calculators. This looks like one of them. So here is the graph of f prime. And it's asking what's true at x equals 2. So at x equals 2, f prime has a value. If f prime has a value, it means f is differentiable there. And if f is differentiable at 2, it's also continuous. So this can't be right. F is definitely continuous at 2 because f prime of 2 exists. It's continuous but not differentiable? No, it's differentiable because the derivative exists. Does it have a local maximum? No. F prime has a local maximum. But what's going on? F prime is positive, 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 positive. F prime is always positive, so F just keeps growing. So D is probably true. F prime is switching from increasing to decreasing, which means, yes, F has a point of inflection. F double prime would be switching between positive and negative. So 32 is D. Okay, 33. So when I see something like this, even before I read the rest of the problem, I will write down h prime of x equals f of x from the fundamental theorem of calculus, because I'm pretty sure I will need that fact. So we want to find the local linearization of h near h equals 3. So I need to know, right? Local linearization basically means find a line. I need a point by taking h of 3, and I need a slope by taking h prime of 3. H prime of 3 is the same as f of 3 from the graph that is 2. H of 3 is this definite integral, which we want to think of in terms of net signed area. It's a definite integral from 0 to 3 of this function f that is being graphed. Intentionally, they want you to notice that these two triangles cancel. So the net signed area comes from that rectangle, and it's -2. So our tangent line, the local linear approximation, has a point at 3, -2, and it has a slope of 2. Y minus the known y coordinate equals slope times x minus the known x coordinate. If we rearrange things, that's y equals 2x minus 8, which is d. Okay, 34. We have a table of the speed of an object in feet per second. And we want to estimate the distance the object travels using a midpoint method with 3 subintervals. Distance traveled will be the definite integral of speed. Okay, so we have 3 intervals, 0 to 6, 6 to 8, 8 to 12, and we're going to use a midpoint approximation. So for this first period, it lasts 6 seconds, and the average speed, or quote-unquote average speed, from the midpoint is 14. Right, and we do have a calculator, so actually I'll leave that. Here, this lasts 2 seconds, and from the midpoint, it's going 8 feet per second. This one lasts 4 seconds, and from the midpoint, it's going 3 feet per second. So I can put this in my calculator. 6 times 14 plus 2 times 8 plus 4 times 3. And I get 112, which is listed, which is a good sign. And that is our answer. Okay, 35. So we have a marathon, and when the winner crosses the finish line, people are behind. And here we have the density of runners. So this is basically saying how many runners we have per mile. So this maybe is very hard to wrap your head around, but this is kind of a rate, right? You can sort of think, here's my finish line, right? And here are all of these people who are trailing behind and approaching the finish line. And as I move backwards, this is telling me the rate in which I encounter runners in the units of runners per mile. We want to figure out how many there are. So to turn a rate, even in this unusual units of runners per mile, to turn a rate into the amount of runners, we take a definite integral. So we're going to do a definite integral of this function. So I just put that in my calculator. I'm only going to need this formula once, so there's no need to teach it to my calculator. Definite integral from 0 to 8. And then I have to carefully type in this thing, 20 times the quantity, 1 minus cosine of 1 plus 0.03 x squared dx, and I get about 166, which is listed, and that is her answer. Be very flexible. You're going to see units you don't know. Runners per mile is weird, but that's a rate. Anything with a per you can interpret as a rate. If we integrate a rate, we can figure out the amount. Okay, all right, arctan is another name for inverse tangent. So we have y equals inverse tangent of 1 over natural log of x. Let me look at that on a graph to see what's going on. Right? In theory, I could probably figure this out, but why not just look at the graph? So I'm creating a new document. I will put in a graph of inverse tangent of 1 over natural log of x. So what this looks like on my graph, and we'll need to think if this makes sense. Here's 1, and it looks like it's doing this. Right? It looks like it has a jump discontinuity, and we want to figure out, does that actually make sense? Right? Or is this a calculator issue? What I'm going to do is I'm going to zoom in to see if these change. So I'm going to change my window. I know this is not helpful if you are not looking at my graph, but I am going to look closer to x equals 1 to see if the graph changes at all. Maybe it actually has an infinite discontinuity and it's drawing it poorly. But when I change my window, it doesn't. Right? The graph is just boop, 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 and then it jumps up here. Right? That's called a jump discontinuity. That's what we're seeing. Right? It's not continuous. It has a discontinuity. Infinite discontinuities are vertical asymptotes. Removable discontinuities is a hole in the graph. This is just plain a jump. Right? And we could think about why by properties of logs and tangent if we wanted to, but we have our answer. Let's move on. Okay, number 37. Okay, so we have g and f related this way. In an interval around x equals a, the graph of f is increasing and concave down, while g is decreasing. So all of these things are about derivatives in some way. Let's start writing things down. So g prime of x would be 2 times f of x times f prime of x. And we want to say something, we want to talk about g using words like concave down and concave up and inflection and things like that. So we probably want to find the second derivative. So let's do another derivative here. I'll just factor out my 2 and I'll do product rule in here. Derivative of the first times the second plus first times the derivative of the second. So now let's think what happens if we plug in a. Around a, we know f is increasing. So f prime of a is a positive number. Okay. We don't know about f yet. We know f double prime at a. F is concave down, so f double prime is negative. All right. What else do I know? We know that, so from this one, we know that g prime of a is negative because g is decreasing. So that's 2 times f of a times f prime of a is a positive because that's increasing. So f of a is actually a negative number. For this to work out, f of a has to be negative. Right? Kind of an abstract problem, but we have enough information to figure out which things are positive and which things are negative. I am noticing that this whole thing is positive. Positive times positive is positive. Negative times negative is positive. Add these, it's positive. Times 2, it's positive. So g double prime is positive, which means the graph of g is concave up at this point. Okay. So we want to figure out c so that we have a local minimum. Local minimum would definitely occur at a critical point. So let's figure out which value of c makes a critical point and then maybe do more from there. F prime of x is, I'm just going to write this as x plus c times x to the negative 1. So the derivative is 1 plus c times negative 1 times x to the negative 2, which looks like this. And we want that to be equal to 0. Or possibly undefined, although if it's undefined, this is undefined. Okay, so what value of c would make that equal to 0? Oh, did I make a mistake here? Oh, no. So we want this to be equal to 0 when we have 3. So f prime of 3 is 1 minus c over 9. We want that to be equal to 0. So we want c to be equal to 9 in order to get, that's the only one that even gives us a critical point. So we will assume it's a local minimum because none of the other answers make sense. 39, I'm back here. All right, so this looks pretty abstract. So what do we know? We have a function where the rate of change is always less than or equal to 4 between 3 and 10. And we have this specific value 7. So here's one way of thinking about what's going on. We have a point on the graph at 7, 8. And what we know is between 3 and 7, this graph is never going up faster than a slope of 4. Right? The slope of the tangent line is always less than 4. So let's see what's possible. Could we have that g of 5 is equal to 0? That would mean the point 5, 0 is on the graph. That would theoretically be possible if we had just a line, right? That line has a slope of 4, which just makes it. The slope would be less than or equal to 4. Right? So this looks like it's okay. That looks like it's possible. Okay. Is it possible for g of 8 to be negative 4? Well, that would mean that we're going way down here to 8, negative 4. We can have negative slopes. So it looks like that's not a problem. Could we have g of 9 is 17? So what's happening is here, the average rate of change would be 9 over 2, which is 4.5. The mean value theorem says the average rate of change always happens for a differentiable function. So if the average rate of change is 4.5, somewhere in between, even if the graph did something else, the derivative would also be 4.5, which is impossible. So this one is not okay. 1 and 2 are possible. I guess if we're being really technical, they can't be true at the same time. No, actually they can. I take that back. But yeah, 1 and C are both possible. 1 and 2 are both possible, so it is C. Okay. At which point on the graph here is f prime of x less than 0? So that means f prime is negative, which means f is decreasing. And f double prime is bigger than 0. So f double prime is positive, which means f is concave up. So where is this function? Decreasing but concave up. Well, that's decreasing but part of a smile. So it looks like it is A. Okay. Inverse functions again. So we want to find g prime of 0. So we need to think g of 0 equals something, f of something equals 0. They have this set up so that it should be pretty obvious, right? F of x equals x to the 5th plus 1 equals 0, which means x to the 5th is negative 1. That would have to be negative 1. So g prime of 0, our rule here is that it is the reciprocal of the derivative of f at the corresponding point. So now we just do a little bit of work. F prime of x is 5x to the 4th. F prime of negative 1 would be 5 times 1, which is 5. So the reciprocal of that is 1/5. 41 is B. Okay, 42. Related rates problem. So we have a right triangle. Hypotenuse is AB. And that's 5. Right? That appears to always be 5. And one leg AC is decreasing, I'm just going to call this x, at a rate of 2 feet per second. So we want to know the rate in square feet per second that the area is changing when AC equals 3. So we know dx dt equals negative 2. This is, in my opinion, too much for you to do in a 3-minute multiple choice problem, but all of the components should make sense. So in order to find the area, I also need to know this. Right, so let's figure out how x and y are related. I know that x squared plus y squared is equal to 5 squared. If I take derivatives, I have 2 times x times dx dt plus 2 times y times dy dt equals 0. And we want to know what's happening when this is 3 and this is 5. Hopefully you remember that that'll be 4. So what's going on at that moment? We have 2 times 3 times negative 2 plus 2 times 4 times dy dt equals 0. So negative 24 plus 8 dy dt equals 0. 8 dy dt equals 24. And dy dt at that moment is 3. So now we want to find the rate at which the area is changing at that moment. Area is 1/2 times base times height, which is 1/2 times x times y. So the rate at which that's changing, right? X and y are both functions of time. We have to do product rule. First times derivative of the second. I usually do the other order. That's okay. Plus derivative of the first times the second. And now let's just plug in everything we know. At that moment, x is 3, dy dt is 3. X is getting smaller at a rate of negative 2. That's a times. Y is 4. So we have 1/2 of 9 minus 8. And, my answer here isn't listed. So can I find my mistake? This happens sometimes. I'm doing these in real time, so if I am making mistakes somewhere, I might not catch it. Oh, okay. So where did that 6 come from? It's 2 times 3 times 2, and I would think I was just thinking that 2 times 3 is 6. So let's see if I can fix things. So if you're going to get something wrong, hopefully you get it wrong in a way where your answer isn't listed. So this is negative 12. So we have, I don't know where that came from. 8 times dy dt equals 12. dy dt is 12 over 8, which is 3/2. So now going over here, my dy dt should have been 3/2. So what we actually have here is, I don't know how to make, there's, okay. 1/2 times, so here we have 9/2 minus 8, which is minus 16/2. So this is 1/2 times negative 7/2, which is negative 7/4, which is listed. That is C. 42 is C. All right, 43. At how many points on the interval 0 pi does this function satisfy the mean value theorem? Remember, mean value theorem is that the derivative is equal to the average rate of change. So what we could do here is we could figure out the average rate of change. My average rate of change would be f of pi minus f of 0 over pi minus 0. F of pi, well, sine of pi is 0, sine of 4 pi is 0, so that's 0. Same if I plug in 0, so it's 0 over pi, which is 0. Okay, this begins and ends at 0. The average rate of change is 0. So we want to know how many times is the derivative equal to 0. My derivative is 2 cosine x plus cosine 4x times 4 by the chain rule. So what I would do here is I would just graph this function. Create a new document. And I will graph the derivative. I will just graph y equals cosine of x plus 4 times cosine of 4x. And I'll zoom in to just look between 0 and pi, right? I can actually just change my window. Change my window settings so that x starts at 0 and ends at pi. And I can just count how many times do I see this graph going through the x-axis. Right, so when I zoom in on this, here's pi, here's 0. The graph appears to do something like so. So how many times is it equal to 0? 1, 2, 3, 4 by my count, which is listed, and that is the answer. In theory, another way of doing this is to look at the graph of the original function and see how many times it has a horizontal tangent. That would probably be equally difficult, right? Or equally easy, maybe even easier actually. All right, 2 more. If the radius of a sphere is increasing at a constant rate, then the rate of increase of the volume of the sphere. So we have to think about, so volume of a sphere is 4 thirds pi times r cubed. On the real AP, they'd give that to you, 98% certain. And so the radius is increasing at a constant rate. So if we start putting rates in here, so here's what we know. We know that this is a constant. So this, and what else is a constant? 4 thirds is a constant, pi is a constant, 3 is a constant. So under these circumstances, dv dt would be some constant, if we group them all together, times r squared. So what does that mean about the rate of increase of the volume of the sphere? This rate of increase is something times r squared. R squared is getting bigger and bigger and bigger. As I put more air in this sphere, I'm thinking of it as a balloon. As the sphere gets bigger and bigger, the radius is getting bigger and bigger and bigger. Square that, that's growing. Multiply by a positive constant. This is growing. So the rate at which the volume is changing is growing. Not only is the volume growing, but the rate at which the volume is growing is growing. Right? This thing is growing, so this thing is growing. The rate is increasing. This is sort of like the second derivative of velocity. Okay, and finally, just eyeballing this, it's not really something the AP would ask, but worth talking about. The rate at which the purification process can remove contaminants from a tank of water is proportional to the amount of contaminant remaining. Okay, so this basically, the rate at which the contaminant changes is proportional to how much is left. So we're going to think of this in terms of percentages, where 1 is 100%. C is how much is in there. No, actually, I take this back. C is how much contaminant is there. So the rate at which we remove it is proportional to how much is there. You should know that whenever you see proportional growth or proportional decay, it is solved by an exponential function. We're going to have e to the kt here with some constant in front. I'm already using C for contaminant. Let's just say this is A. This is what this function is going to look like. Okay. So 20% can be removed during the first minute. So what that means is if we plug in 1 minute, we'll be down to 80% of the starting value. And the starting value is A. So C of 1 on the one hand looks like this, and on the other hand, that's 80% of A. So we would have e to the k is 0.8, and k is the natural log of 0.8. So our formula looks like A, which is our starting amount, times e to the natural log of 0.8 times t. Now, we want to know, right, 98% must be removed for it to be considered safe. So safe is when we are at 2% of the original. Again, I feel like there's a little too much going on here in terms of you really understanding the conceptual stuff of specific exponential growth and decay for this to be a fair problem. Sometimes the practice books are a little unusual. So we would solve this. The a's cancel. We have e to the natural log of 0.8t equals 0.02. Take a natural log of each side. I can divide, so t would be the natural log of 0.02 over the natural log of 0.8. Do not try to cancel those or invent your own log rule. Just type it into your calculator as is. There is theoretically a rule for redoing that, but why bother when you can just type into your calculator something that you are 100% sure is correct. And I get that this is about 17 and a half, and 18 minutes is a choice. Okay, there we go.